Good all. I hope you all are safe and sound. Today is my 35th lecture, and as you can understand and see, I've managed and persevered to come from a redundant technology to the latest technology. Took me a lot of perseverance to come up with the latest so I'd be able to reach you out in much more effective manner. Again, my mantra is stay safe and stay at home and stay away from the Chinese Wuhan virus and boycott the Chinese products. Coming to my lecture number 35, where I've taken the cognizance of quite a few of my viewers, mariners, and comrades to impart and or continue with the same thing what I started as a lone ranger on the subject matter of the hydrodynamics and ship handling. Kindly do visit my channel under the banner of Marine Quest Solutions. Please do like and subscribe it. And today, as we speak, the subject matter is about the importance of hydrodynamics in ship handling. Today, we are going to share the salient features and talk about the points which we need to ponder as far as the subject matter of importance of hydrodynamics in the ship handling is concerned. So we begin. First and foremost, again, the subject matter importance of ship hydrodynamics in the ship handling. Uh, Coming to this thing, remember when we talk about the ship handling, what is the main mantra? The main mantra is to amalgamate, cohesively harmonize the external and internal forces because internal forces lie on board the ship, be it your steering, your main engine, your maneuvering characteristics, and if smaller vessels, you may have a bow thruster. So the main mantra is optimization of the external forces to your advantage, and it's basically the interface of man and machine. That's where the man has to excel. But prior to that, we have to know the nitty gritties and the characteristics of the machinery, what we are working upon or we are handling. Now, as we speak, when I took this subject matter of hydrodynamics and ship handling, because after being in command for almost two odd decades and being a mooring master for 4 odd years, right now, today, what we are facing is basically the errors or the glitches or the human factors, which is basically culminating into horrendous circumstances of accidents, collisions, groundings, lots of other things. So, the issue related to the vessel's maneuverability and the ship handling are among most frequent causes of accidents at sea. A recent analysis, which I've taken from after doing loads of research, we call it CRG, that is collision, ramming, and grounding. Ramming is collision, grounding basically when two ships ram into each other. The casualties for this subject matter are they account to approximately 53% of all the accidents leading to the ship's loss. Now you can understand. Ship's loss means from the from the insurance point of view, maybe a total constructive loss, but the main point of it from the SOLAS is the loss of life and loss of environment or the damage to the environment, and then comes the property. So when we talk about the safety, safety takes the predominance over and above all aspects we talk about the human life. In turn, 70 to 80% of these collision, ramming, grounding casualties are attributable to the human organizational errors, that is HOE, and the fact that indicates that these kind of errors warrant special attention. When we talk about they warrant special attention, it means a specialized courses on ship handling, maneuvering, etc. Just to share with you, I've been also conducting loads of lectures for mariners around the world on hydrodynamics, ship handling, and STS ops. Because today, what is happening? Be it owner, charter, whether manager, and or the seafarer, what is hitting you below your belt is the errors in the safety towards the navigation, wherein which the prudence shall always be exercised. Therefore, according to some of the studies, combined to the design of and the construction faults that impair maneuverability and the force majeure is responsible for 20% of the human and organizational errors. We understand that there have been some design faults with the ships where we can understand that, the shipyard or the naval architecture has to be kept accountable for. But end of the matter is man and machine interface. How we can take uh, adversities into our advantage, and that's what I talked about in the first or second section regarding man and machine interface. That's must. Coming to the next point, as indicated by the figure, remaining 80% is attributed to such operational factors such as the pictorial thing which has been talked about here is CRG casualty, what we talked about, the collision, grounding, and ramming casualties versus the safety culture. The safety culture of the company, of the organization, it goes down the rung to the to on board culture or the to the master and the crew respectively. Then comes the human error or human performance. Now, when we talk about the human error or human performance, is basically how are we trained, how well we are trained, how well we are appraised. Of course, as I said earlier, the organization is also to be kept equally accountable on the subject matter, and the system what we are promulgating. Because from our perspective, our point of view, the chalta attitude has to be abolished. It is basically to be made redundant. We need to walk the talk and come to the subject matter of knowing the subject. It's only when we know the subject and we need to pull up our socks, we will be able to perform better. Because remember, our shipping world also comes under top 10 cadre of the professions in the world. That's where we have to basically demonstrate our competence to survive in the industry, beat any national, beat any national. And I'm not prejudiced about any national when we talk about the seafarers community. The next point I'd like to highlight is what actually are the main factors when we talk about the hydrodynamics. In my previous lectures, I have discussed a lot on the different subjects, be it the hydrodynamics, ship handling, on the various lectures. Today, this one is the 35th lecture. I thought of giving a little appraisal just to refurbish or brush up our knowledge. First and foremost, the things which affect the hydrodynamics are, as stated here under, the resistance to the ship's hull through the water, that is, the bow and the stern waves. If you have been following me up and if you have been watching my channel, please do check first few lectures where I have explained in a conclusive and objective manner what are the bow and stern waves and why the bow waves are construed as positive and stern waves are construed as negative. I'm not going to go in details because these are the main factors associated in amalgamation of the ship handling and hydrodynamics. So, the bow waves are construed as positive. Why? Because the vessel is when she's moving, making her way ahead and or at anchorage, the tide, because even when the vessel is at anchorage, she will stem the tide and or the wind. She'll take the resultant. She will still have the similar kind of a hydrodynamic thing with respect to our sailing when she's sailing or when she's underway. So the bow waves are construed as positive and stern waves are construed as negative. Coming to the point number two, the water pressure exerted on the ships. Of course, that goes with physics. The pressure is equal to depth into density. The density of water and the how much is immersed. That's what sustains the pressure, and that's what we also see in a even lubricator, the bearing, the bending moment, and in particular the shearing forces, which are because of the external forces or the pressure sustained by the vessel. So all these things are basically trying to restrict the maneuverability one way or the other, be it the SF or the BM forces and or the hog and sag as far as the ship is concerned. The hull shapes and design, as you know, for a vessel which has a block coefficient of less than zero point 0.7 will squat by stern, and for the vessel which will have a block coefficient more than zero point 0.7 will squat by head. That also goes with the coefficient of fineness along with the block coefficient. Now, when we talk about this particular thing, you would know that most of the container vessels, cargo vessels, passenger vessels, their bows are very much streamlined. However, when we talk about the big tankers, VLCCs, ULCCs, Suezmax, Aframax, we have a bigger, larger bulbous bow as per the cargo requirement because the same amount of liquid is to be loaded equivalent to a dry cargo ship from the metric tons because the volume is more, and that is the reason the tankers they have a bigger or the broader they have much more broader beam with respect to the dry cargo ships. So the hull and design also matter when we talk about the hydrodynamics, ship's maneuverability, etc. Now the vessel's draft in relation to the available depth of water. This plays a major factor. When your draft and depth ratio is approximately twice, in other words, if your draft is 10 meters and depth is 20 meters, the effect of hydrodynamics and or squat will be very much prominent. Out at sea in open ocean, because we have lots of depths. I'm talking about open ocean. So we do not realize that. But when we come to critical passage and or restricted waters, where in which the depth and the draft ratio is 1:2. In other words, 10 meters depth draft and 20 meters depth. you will realize, you will find lots of things, lots of abnormalities, be it your steering helm, be it your turning circle, all these will be affected some way or the other. And when the depth reduces below that, it will be, the enhancement of these factors will be much more than what we would not expect in open oceans. Coming to point number uh, 4, the density of water. Now we know that whenever the vessel traverses from one density of water to another, besides the mean sinkage, there is also a change in the trim. Now, when we talk about, which is also I've highlighted in the next point, point number 6, you see the weights on board the ships are fixed. We don't change the weights once we depart the load port till we arrive the discharge port, till we discharge the cargo. But with the change of density, the underwater volume of displacement, when we talk about the underwater volume of displacement, I'm not talking about the mass, changes. And that's where the center of gravity and center of buoyancy, they keep, come to this thing to change their position. Because when we talk about center of gravity is the total mass loaded on the ship, which remains constant as long as we don't change the weights. But the center of buoyancy, in an opposite manner, or can be construed as a center of gravity of the underwater volume of displacement. So when a vessel enters from one density to another, because of the change of trim, the center of buoyancy shifts. Let's say you departed from a port in an even keel, in a seawater port, but when you come to the discharge port in a freshwater or a brackish water port, because of the change in the underwater volume of displacement, the center of buoyancy will shift. So center of gravity will not shift as long as the weights are still, constant, what they were when you departed the load port. That will affect the change of the trim, and also will affect your ship's maneuverability and ship handling with respect to the hydrodynamics. Because when we talk about the hydrodynamics, it's concerning water. Coming to the next point, like internal distribution of the weights, which affects vessels' center of gravity and center of buoyancy, which I've already explained. Vessels trim and list. The vessel, of course, trim whatever trim she may have, and the trim effect, what we talked about, the change in the due to the change in the density of water, the trim change may take place. But in case the vessel has a list, also will also affect her or hamper her maneuvering capabilities with respect to the maneuvering curve, which has been, like, tried and tested during the ship's trial, uh, when the ship is delivered from the shipyard. Coming to the next point is vessels waterplane area. Waterplane area, of course, goes with the hydrostatic particular. Like whatever draft you have, the waterplane area will changes, because when we talk about the ship, she's, narrowed at the bottom at the keel, and she broadens up as she goes up, and then until the paddle body, she broadens up, and then she remains same. So the waterplane area also plays a role in the ship's handling with respect to the hydrodynamics. Point number 9, the pivot point or pivot axis. We know the pivot point or pivot axis lies at almost midships, approximately in the position of center of flotation when the vessel is stopped. From that position, it moves ahead to approximately one third of the vessel from the bow when the vessel is making a headway through the water. Now, somebody may ask me that why does it not go directly forward? And that's where approximately, because this is a virtual point, this is because of the water pressure exerted on the ship's hull or the bow. It approximately stays steady to approximately one third of the length from the bow when the vessel is moving ahead. The same pivot point, when the vessel is going stern way or on a stern motion or stern movement, the pivot point will shift approximately to one third of the length from the stern. A live example, because whatever I'm imparting is based on a practical, pragmatic experience. Now, think about it, when the vessel is approaching an anchorage and when the vessel is giving a stern kick. Good old days when we did not have the high tech technology of GPS or hand or speed over ground. When we are giving a stern kick, we used to go on either side of the bridge wing, looking at the tide and the wind. Basically, when the vessel is approaching towards an anchorage, she will settle in a vector in between the tide and the current. That is subject to lots of other factors, mainly because of the windage area, the ship's uh, uh, over water or the exposed area to the wind and the tide, whichever is stronger, she'll form a resultant vector and settle down. When we are heading into that direction, let's say we have aligned the vessel to the resultant vector, because she'll automatically come when the vessel speed is less. And at that point of time, when you give the stern kick, you will find that when the water is receding towards approximately bridge wing or maybe a little forward of it, which is approximately one third of the length from the stern, as per the LBP of the vessel. The vessel speed will be zero. If you can check, you if you want, you can check it on your GPS or on your egg disc or radars. This is the practical seamanship what we are talking about. The next point is vessels displacement slash underwater volume of displacement, what I talked about, because the underwater volume of displacement plays a major role. Let's say there's a small vessel, mid-sized tanker around 40, 50,000 tonner, and there's a VLCC. If they're coming together, means overtaking situation or in the narrow channel. I've explained in my previous lectures also, that is when uh, what happens when we take, hypothetically speaking, if we take out those two ships, away and put them on the table. That's what I've explained in my YouTube first or second and third lecture. Please have a look at it to get a better understanding. What happens? Water finds its own way. A vessel which is a VLCC is traversing through let's say a restricted water will have a bigger underwater volume of displacement. When she's moving, the water which is coming from ahead from the bow is of more quantum, more quantity to fill up the void of the underwater volume of displacement. In contrast to the vessel, a mid-sized tanker, 40 or 50,000 tonner, which is displacing less water, and her underwater volume of displacement is also less, will have a horrendous amount of time if she's close in the vicinity of a laden VLCC. Besides having an effect of her steering, she may also have a lateral drag towards the VLCC because of the vacuum created by the VLCC's underwater volume of displacement. Please do check my previous lectures to have a better understanding. And in case you have further doubts, please do let me know on my YouTube channel. The next point as we proceed further are, one sec, I think I missed out. Okay. The other thing when we talk about the vessel's uh, internal factors, that is vessel's main engine and the steering capabilities. Some vessels have very good maneuverability because of the main engine and the rudder what they use. Like one of the best rudder which is got which gives the vessel very good maneuverability is a Becker rudder. So vessel's main engine, how efficient, how fast. Like for example, a container vessel with a Becker rudder and bow thruster does very good maneuverability in ship handling. Or if we talk about the same kind of vessel, vessel with the same dead weight, let's say tanker, a big tanker, she may not have those kind of features. So her maneuverability may be little, not so fast, maybe a little sluggish with respect to a container vessel. So when we talk about the main engine and steering, these are the internal factor. Now, the idea when we actually started this particular session, I said how we can optimize, harmonize, and take the advantage of external factors because we cannot control the external factors. We only have the control of internal factors. That is the ship's main engine, her steering capabilities, her rudder, and the maneuvering characteristics which has been delineated by the shipyard. Now, how we can harmonize and how we can cohesively work together, and that's what is the art of ship handling. Trust me, with my personal experience, what I know that ship handling things are never taught by books. Is basically the man and machine interface. How can you get into that kind of a paraphernalia by virtue of which you can think about it, how to handle her with your best thinking capabilities and with your past skills of the maneuvering what you had carried out on your probably past vessels. This I'm sharing with the masters who had been, on the same hot seat where I had been also, or I had been also until last few months. Now, the other thing which is the vessel's propeller, it could be left hand screw, it could be right hand screw. You guys can check it on your ship's maneuvering characteristics or the IMO requirement where you have to have a ship's maneuvering characteristics details on the bridge. A vessel with the left hand screw, you will always find she has a small turning circle when she's turning to harder port with the main engine full ahead. Why? Because the vessel with the right hand screw, I stand correct. The vessel with the right hand screw will have a smaller turning circle when she's turning to port. Why? Because of something known as centrifugal and centripetal forces to equalize that. Whereas the right hand screw, same vessel, when she's turning to starboard, she will have a bigger turning circle, and vice versa. Okay, ladies and gentlemen, I conclude over here. And in case you have any doubts or anything, please do let me know. Thank you very much for liking and subscribing my channel because whatever I'm doing today is basically, impart my legacy with my on hand or hands on experience with the ship handling, with pragmatic things, what I've done in past. And I thank you very much. Please do like and subscribe my channel. Thank you and good day.